In this video, we're going to look at acceleration near Earth's surface. And we have two main learning goals. So first, we'll be able to explain acceleration due to gravity, air resistance, and free fall, and you'll be able to perform calculations using the force of gravity, or the acceleration due to gravity, and vertical acceleration. So here's just a few notes on acceleration due to gravity. So we use this as our constant value. It does change a little bit depending on how far away you are from sea level, but in general, we use the acceleration due to gravity at 9.8 meters per second squared. You'll see it's a negative value because gravity is pulling us down, but often we put it in as a positive value and then assign our directions at the end of our calculations based on some prior knowledge. So what we're going to do is we're really just going to look at the calculation portion of this lesson. The rest of it you can read your textbook to figure out all of the other part, the free fall and air resistance and such. We're just going to look at a couple of examples, and what you're going to find is that we're going to go back and we're going to be using those 5 key equations for constant acceleration to solve these problems, and just we're not going to be given the acceleration because it's going to be acceleration due to gravity. So let's look at this example. A glass is dropped off a balcony and accelerates uniformly to the ground. If the balcony is 15.0 meters above the ground, how long does it take for the glass to reach the ground? Assume there is no air resistance. So let's read back through and write down what we know. So the glass is dropped off a balcony. So therefore, our acceleration is equal to our g, which is negative 9.8 meters per second squared. We're going to assume a couple of things. First of all, that its initial velocity is 0. So we're going to assume that somebody wasn't throwing it off the balcony. And we're also going to assume that when it hits the ground, it also comes to a stop. So in this case, we actually know both of our V1 and our V2. We know our delta D, it's 15 meters above the ground. So when it hits the ground, it will have traveled 15 meters. And we're being asked for our delta T. So what you're going to do is you're going to go and consult those 5 equations that are on your formula sheet and choose one that will work for this equation. So the one I've chosen is this formula. And we're going to rearrange this first, and what you should notice is that this whole term is going to go away because our V1 is 0. It just makes rearranging this a whole lot easier. So I've got this now. And what I'm going to do is I'm going to multiply both sides by 2 to get rid of the fraction because nobody likes fractions. So we'll have 2 delta D equals a delta T squared. So then we're going to divide both sides by a and take the square root, and that will get us our delta T. So our rearranged formula is this. Okay, square root. I'm sorry, apologize, the writing is a little bit messy. So we'll now sub in our information. And again, if you want to leave the units out, that's fine. And we want to round so that we have 2 significant digits, so we get 1.7 seconds. So in this next example, it's asking us, so it's part 1b, so everything's still the same. So now it's asking us, what is the final velocity just before it hits the ground? So now our V2 is what we are looking for. And everything else is going to stay the same. So we still have our acceleration. We still have our V1 as 0. Now we know our delta T. So we could use an equation that now has delta T. And we know our delta D. So again, go and check out your equations. Since we're trying to solve for V2, we might as well use the equation that's already set that way. Then we don't have to do any rearranging for our work. So we're going to use that equation. So let's go ahead and put our information in. So we get 294, and then we need to take the square root of both sides. So our V2 is 17.1 meters per second. We only want 2 significant digits, so we're going to round that to 17 meters per second. So that means the glass just before it hits the ground is traveling at 17 meters per second. Again, if you want to go ahead and add a direction, I guess it would be down. You'll see that sometimes, even though these are all vector quantities, we don't always include a direction. So let's look at another example. So a tennis ball is thrown straight up in the air, leaving the thrower's hand at an initial velocity of 3.5 meters per second. How high from where it was thrown does the ball go? So what that means is that you'll see in this picture, and that's why I've included the picture, we don't care about that part. So we don't care, we just want to know how high does it go. So let's write down what we know. So it says that it's traveling with an initial velocity of 3.5 meters per second. And as it's coming back down, its acceleration is going to be 9.8 meters per second squared. Now, the other thing that we're going to have to start thinking about is that when the ball gets to the very top, so think parabola shape from math class, when it gets to the very top, for a split second, it actually stops before it changes direction. So that actually means that our V2 there is 0 meters per second. So just before it's going up, it has to stop before it can start coming back down. So at that very top of that parabolic motion, we actually have a V2 of 0. Okay, so you're going to have to start realizing those things because otherwise you're going to have a hard time choosing your formulas. And we're being asked to figure out our delta D. So you need to go and use the formula that does not have t in it. And that is this equation. So we are going to rearrange this equation before we start. So we're going to take our V1 over first. So we're going to subtract it. And then we'll divide both sides by A. Sorry, I forgot my arrows. Okay, and then I'm just going to rewrite it in the other direction for you. And then we can go ahead and put our information in. So we have 0, we have 3.5 squared over 2 times 9.8. So you put that all in on your calculator and you get 0.625 meters. So then we go and check, we only want 2 significant digits. So that gives us 0.63 meters as our displacement. So that's our final displacement there. Part B is asking us for how long it takes for that ball to reach its maximum height. So we're looking for that point right there. So again, all of our information is going to be the same. Okay, so we have V1, 3.5 meters per second. We have our V2, 0 meters per second. We have our acceleration due to gravity. We have our delta D now. We figured that out. Okay, so we've got, again, a bunch of different equations that we can use. Let's use this equation. Just in case we made a mistake there with the first one, if we use that equation, we're not using the delta D that we just calculated, and then if we made a mistake, we'd be better off. So again, let's rearrange this equation. So bring the v1 over, and then we need to divide by a. So to figure out our delta t, we're going to do v2 minus v1 all over a. And then we'll put our information in. And we're going to round so that we only have 2 significant digits. So we get 0.36 seconds. Now, if you were to leave that as your negative and you don't put a negative in for your acceleration due to gravity, you'd in fact calculate a negative time. And then you have to stop and ask yourself, can I have negative time? And the answer to that question is no. Time always has to be positive. So in that situation, the easiest way to make that positive would be to put that negative value in there for our acceleration due to gravity. Or just leave it as positive and then remember that you cannot have a negative time. So that's a quick review of the calculations that are involved in acceleration near Earth's surface. So hopefully you're good with this second learning goal. The first learning goal really is just a matter of reading in your textbook. So hopefully this video has helped clear up some issues with the calculations dealing with acceleration due to gravity.